Okay. So welcome everyone. Welcome to the second lecture on radiations. In the yesterday's lecture, we started radiations and we started with the understanding that radiations should contain electric field and magnetic field, which are inversely proportional to R. Okay. And then we said that, okay, we solve the problem of the oscillating dipole, in which the dipole moments, electric dipole moments are oscillating. And we studied the formula for electric field, magnetic field, and then we did the formula for Poynting vector, and in the end we did the formula for power radiated. So 4 formulas we did, and I gave you the page of the formula, and that has also been shared with you in the Telegram channel. Today we are going to discuss 2 more problems, and one of them is known as the magnetic moment radiations, and one of them is the moving charge. And we just need the formula out of it. So these formulas are taken from the Griffiths book without the derivation. Derivation is pretty much long one, and that does not give us any advantage to do that derivation. If you want to go through the derivation, you can go for the Griffiths book. So number one thing that I want to tell you is that what if the magnetic moment is changing? Now, what is this magnetic moment? So let's say you have a current carrying loop. So you have a loop, and this loop has some current I. Whenever you have a current, you have a magnetism. Whenever you have a current, you have a magnetism. And magnetism never comes alone. Magnetism is never alone. It always have north and south pole both. Electricity can come alone, means positive charge can exist alone, negative charge can exist alone, but magnetism can not be alone. It will always have north and south both. How do you visualize this? How do you see that, okay, it has north and south both? So if you look at this loop from the top, you see there is something south polarity. You can say clockwise current. If you look at this loop from the top, you see clockwise. And clockwise basically means south. But on the other hand, if you try to look at this loop from the other side, you will see anti-clockwise. And anti-clockwise basically means north. Let me show you if I have that still with me. I also did the same thing to show in the you can call it in the, we did the same thing in the parity experiment as well. So let me just show you just a second. So let's see this. So can you tell me, what do you see, clockwise or anti-clockwise? What are you seeing right now on your screen? Clockwise or anti-clockwise? Clockwise. So right now you see clockwise. Okay. Clock. Now let me turn this page around. Now what do you see? It's not that much stronger, but what do you see now?
Anti-clockwise.
Anti. So you see, by turning the page around, once I showed you from the front, so you get a clockwise view. And once you look at the thing from the behind, you get an anti-clockwise view. It means from the front side, it has a north polarity. From the back side, it has a south polarity. So magnetism is coming together. So whenever you have two poles, you call it as a magnetic dipole. Dipole. And you define the magnetic dipole moment. In the same way, you have an electric dipole, negative charge, positive charge. You become an electric dipole, and then you define an electric dipole moment. Similarly, in this case, you have a north pole, south pole. As a result, you get a magnetic dipole, and you define a magnetic dipole moment. And magnetic dipole moment is defined as current into area. So you have a current and you have an area. You see, this is an area, pi r square. Area of a disk, pi r square. And you also have a current I. So magnetic dipole moment will become current into area. That is the definition. Okay. So if I say m naught, it means the magnetic dipole moment at time t equals to 0. Okay, so it is simply current into area. And once you have a magnetic dipole moment, another possibility is that this magnetic dipole moment may be changing with time. If it is changing with time, then you will have the radiations. If this magnetic dipole moment, let's say current is changing, so magnetic dipole moment is changing. So if the magnetic dipole moment starts changing, you get a radiations. You need two things. One of them is known as the intensity. Intensity is also known as the average of Poynting vector. We discussed this yesterday. Average of Poynting vector. Okay. So that is given by this formula. And this formula is very important to us. Point to point, this formula is very important. You need to memorize this formula as soon as you can. You need to bring up some things. You can say is it is inversely proportional to r square, directly proportional to sine square theta, omega 4. But you also need to remember the constant values. Very important. And the second thing that is very important is total power radiated. So this is intensity and this is power. And power is given by nu naught m naught. M naught is a magnetic moment at time t equals to 0. Okay. So these are the two formulas. Any doubts, anyone? Any doubt? Anyone having any problems or any doubt? Clear, everyone? This formula is important. And why these radiations are coming? Because magnetic moment is changing with time. Yeah. So clear, everyone? What do you say? Yeah. Perfect. Should I move on? So you can spend a little bit of time in remembering this formula, in noting this down, right? And if you need a full proof, you can go for the Griffiths book. Okay. Yeah. Current in the loop must be changing. Otherwise, magnetic moment will not change. If there is some other way to change the magnetic moment, that is also fine. Without changing magnetic current, if we change the magnetic moment, let's say we are changing the area, or let's say we are changing the direction, then also it is fine. Okay. You just need to change the magnetic moment. Okay. So let's talk about another fact. Sometimes they ask you about the ratio of magnetic power and electric power. So the ratio of magnetic power to electric power is m naught by p naught c whole square. M naught is a magnetic moment at time t0. P naught is an electric dipole moment at time t0. C is the speed of light, and you square it. And if you will calculate these numbers, you will come to realize that electric power is much larger than magnetic power. Magnetic power radiated is very small as compared to the electric power radiated. Because when you will calculate this number, this thing will come out to be much less than 1, which basically means that magnetic power is much smaller than electric power. Okay. So this was the first category of the problems which can be asked to you. So if the radiation question comes and if it is within the limits of the difficulty, three categories of question can be asked: oscillating dipole, oscillating magnetic moment, and moving charges. Out of these three, going beyond this could be a difficult thing. But if our luck is good and the paper is within the reasonable levels, then these three topics are important. Going beyond this is a stupidity. Doing the entire chapter line by line will just waste our time. Okay. So I have already gone through the entire chapter. It took me almost 3-4 days to go through the entire chapter. And I'm just teaching you whatever is required because you have a lesser time. So right now, if I start doing the derivations for 10 days, we will just keep on doing derivations of this chapter only. Okay. So take from my experience and just focus on the important part. Then comes the moving charge. I said that if the charge is stationary, it produces electric field. If the charge is moving with constant speed, it produces magnetic field plus electric field. And if the charge starts to accelerate, it produces radiations. So if the charge is accelerating, radiations are produced. How much? So this is the formula. Again, the two formulas are required: intensity and power. How much intensity? Nu naught q square. Q is the charge. Acceleration square. A is the acceleration. 16 pi square c. So 16 pi square c sine square theta by r square. Again into r cap. Again, if you do for the power, if you go for the power, it is nu naught q square a square by 6 pi c. So two formulas are there for the moving charge. So if your charge is moving and it is accelerating basically, then it will radiate the power, it will radiate the radiations, and the formula for those radiations is he can either ask you about the intensity or he can either ask you about the power. So these two are the formulas that you will use. Yeah. So next I will begin with the problems. Any doubt, anyone, please?
Sir, if we just memorize the pointing vector, is there any way to like calculate the power from it?
Yes. If you do this thing, you get power.
Okay, sir.
Yeah. Perfect. Yes. 110% right. This is what we did yesterday, right? We learned that this is a formula. Okay. So now let's do some of the problems. These are basically CSIR-NET PYQs. So an oscillating current is given. So a current is oscillating and it is given and it is flowing along the y-axis. Perfect. And it is passing through the thin metal sheet of area. This area is given. What is the total rate of total energy radiated per unit area? Can anyone tell me what is this thing? What they are asking? What they are asking basically?
Power.
The rate of total energy radiated per unit area. Energy per unit area per unit time is known as intensity or power. What are they asking? Tell me.
Intensity.
Energy radiated per unit area per unit time. So what they are asking is
Intensity.
you can find power and then you can divide by area. You will get your answer. So rate means divided by time. Total energy is U divided by area is this thing. This thing. So U by T is known as power. And if you divide your power with area, you basically get your intensity. Okay. So you basically get your intensity. So let's begin with our formula. So which formula should we use first? So this is our power formula. So let's use the power formula, or you can even use the intensity formula as well. So I'm here using the power formula and then I will divide by area. So I will get my answer. Okay. So this is my current and my magnetic moment is defined as current into area. Perfect. So current into area, I naught, and what is my current? Current is I naught e raised to power minus iota omega 2. And if someone asks you what is a magnetic moment at time t equals to 0, so I put my time 0. So I get I naught into A. And then I bring my power formula. So power formula is nu naught m naught square by omega 4, 12 pi c cube. So this is a formula I'm bringing from here. You can clearly see. Once you have this formula, then you get this power formula. Okay. And then you basically put the value of m naught. You get I naught square A square omega 4, 12 pi c naught cube and so on. You need basically power per unit area, so you can divide by area, so you will get A. Okay, anyway, let's not go to power area because area is anyway 1. You can clearly see area is anyway 1, so let's forget about area. So this is going to be 1 centimeter square, right? They are not asking about the powers here. They are only asking about the overall structure. They are not asking 10 to power how much. Okay, so then here what we should focus here, area is anyway 1, so let's ignore the area. So we get I naught square, okay, I naught square A square omega 4, 12 pi c cube. Now my answer is not in terms of nu naught, my answer is in terms of epsilon naught. So in magnetism, you have nu naught by 4 pi. In electricity, you have 1 by 4 pi epsilon naught. If you ever have to go between them, you can go between them. So nu naught by 4 pi and 1 by 4 pi epsilon naught in radiations. Whenever the constants does not matter and you just have to go from one to other. That's just I'm saying. That exact constants does not matter. How much 2, 3, 4, 5, 6 number does not matter. And you only have to go for one parameter to others. So you can replace your nu naught by 1 by epsilon naught. So that is exactly what I'm going to do here. So I'm going to replace my nu naught with an 1 by epsilon naught. Right? You know the constants. In magnetism, you get nu naught by 4 pi. When you write Biot-Savart's law and so on. And in electricity, you get 1 by 4 pi epsilon naught when you write electric field and so on.
Sir,
Yeah, please. Yeah.
in this power formula, where is 12 coming from?
This formula I'm using. No? This I'm using.
12 pi. Oh, yes, yes. Thank you.
Yeah. Okay. So then, okay. So I replace my 1 by nu naught with 1 by epsilon naught. And area, since I'm ignoring because it is 1. So, but I'm left with this I naught square omega 4 12 pi epsilon naught c cube. And if you look at it, this will be option number D. Okay. Main thing that was exciting to do here was how does it depends upon I naught square, I naught and omega. I naught square omega 4, I naught omega, I naught square, I naught omega cube. So from our formula itself, we know it depends upon I naught square into omega 4. Because our formula says that it depends upon magnetic moment square and omega 4. And in magnetic moment, you get I naught. So you get I naught square and you get omega 4. So without even doing much math, you can even say that option number D will be. So this was one of the question which could be asked in a CSIR-NET. Any doubt, anyone, please? Even if you use the first formula, you will get the similar result. Because that also depends upon m naught square omega 4. And this also depends upon m naught square omega 4. So from m naught, you will get I naught square and omega 4 is omega 4. Still you will get option D. Okay. Yeah. Any doubt, anyone, please?
Sir, can you explain again how you replaced E mu 0 with 1 by epsilon 0?
Yeah. So okay. There are two methods to go from one to other. One is using this. Okay. And another is if I don't care about the exact numbers, then what I know is that I can make an analogy. In magnetism, when you write the magnetic field, you get nu naught by 4 pi I dl by r cube. Or if I write the magnetic field due to the magnetic dipole moment, you will get nu naught by 4 pi 2m by r cube. This is because of the magnetic dipole. And this is because of the electric dipole. So magnetic moment is doing the work of electric dipole. M is doing the same work as P. Nu naught by 4 pi is doing the same work as 1 by 4 pi epsilon naught. So whenever you do the magnetism, you get nu naught by 4 pi. Whenever you do the electricity, you get 1 by 4 pi epsilon naught. Right. Sometimes when we compare gravity and electrostatics, we say that capital G is doing the
So,
same work as 1 by 4 pi epsilon. Yeah.
so it's an analog, right?
Analog. Yeah.
Okay, okay.
Yeah. It's an analog because
I
they
thought
need an
I thought
answer.
they were yes, sir. I thought they were somehow equal.
No, they are somehow equivalent as well because if you go for this formula, right, this is an actual formula. So then if you square it both sides, then also you will realize that epsilon naught and nu naught are inversely proportional.
Yes.
Right. But then another C factors will come and which is not in our problem. So I did not go through the C part because then that will change our C terms. Okay. So I made an analogy. So I said nu naught can be replaced with 1 by epsilon naught. So that's what I just did. Okay. Yeah.
Sir,
Any doubt?
also,
Yeah, please. Yeah.
also, how is this? How does I0A give the magnetic moment here? So usually when a current bounds a certain area, then we get magnetic moment, right?
Yeah. So in this, the current is there. So in this, the magnetic field lines will be like this.
Yes,
So
sir.
if you look at from one side, you get a north. If you look at from other side, you get a south, right?
No, sir,
So-
I mean, mathematically, how is it equal to I0A?
Mathematically, magnetic moment is always defined as current into area. You are saying that it should be like this?
Yeah, so that's the only thing I know. Yeah.
No, no, this will be used as IA.
Okay, sir.
Yeah. Okay.
That's
Yeah. Tell me.
sir, and the question they said that calculate the rate of total energy in the distance of 100 meters. Sir.
Yeah. Okay. Yeah.
If the same question asked at the distance of infinity, it's
No.
the same answer
No.
is
If they ask you to compare it, and okay, why I didn't choose that approach? Why I did not went behind this number? Because in my options, I just have to focus on this thing. But if they, let's say 50 and 100 matters, then you have another formula. No? Then use this and put R as 100, and either otherwise put R as 50. Right. So then you can go behind that. What do you say?
okay.
Yeah. So both the formulas are available for our disposal, whatever we need. So this is not a only solution I'm saying. You can think of it in any terms, right? Okay. Then comes the next part. So this question, a non-relativistic particle of mass m and charge e is moving with the velocity v vector and acceleration a vector. It emits the radiation of intensity I. Intensity basically means this thing. What is the intensity of the radiation emitted by the particle of mass m by 2, charge 2e, velocity v by 2, and acceleration 2a? So let's go to our formula. So intensity. So they are asking this. So I will use this formula, and since it is a moving charge, I have to use that. So the formula is coming, which is nu naught q square a square by 16 pi square c sine square theta by r square. I'm not changing distances. I'm either the charge is changing, acceleration is changing. That's all. So intensity is only depending on charge and a in this case, because I'm just changing the particle, mass of the particle, charge of the particle, velocity of the particle, acceleration of the particle, and so on. Anyway, the mass and velocity does not comes in the formula. Acceleration comes in the formula and charge comes in the formula. So your intensity depends upon q square a square. Even r square does not matter. So I do I2 by I1. So second charge has a charge of 2e. Second charge has a acceleration of 2a divided by first charge has a charge of e and acceleration of a. So 2e square 2a square divided by e square a square gives you 4 is 16. So I2 becomes 16 times I1. So your option number A is correct. Done? Clear everyone? Easy question, nothing else. So if this kind of question they ask again in the net, at least you should be able to do that. Okay. So at least we should be above average, right? At least we know the above average in radiations. Okay. Yeah. What basic? Clear everyone? Should I move to the next problem? Any doubts in this one? Okay. Now this question is little tricky. Not little tricky, but the language of this question makes it tricky. Language of this question makes it tricky. Other than that, everything is fine. So they say that electron is deaccelerated at a constant rate. So the acceleration is constant. And it starts from initial velocity u, and the final velocity is u by 2. And obviously it is non-relativistic because u is much less than c. When it goes from u to u by 2, it covers a distance of s. So when you are driving a bike and you suddenly try to reduce your speed, when you are reducing your speed, you will cover some distance, right? So they are saying that amount of energy lost to the radiations. Okay. Energy, when you heard about energy, you get power into time, because power is energy per unit time. So energy becomes power into time. I can find power because I know the formula. I can find time because I know the simple kinematics. But before that, let me find the acceleration. So I will use the equation v square minus u square equals to 2as. Final speed is u square by u by 2, so it becomes u square by 4. And initial speed is u, so u square and 2as. From here, acceleration becomes 3u minus 3u square by 8s. Now I also need time, so let's again use this same thing. And v equals to u plus at. Final speed is u by 2. This is u, and this is a, and this is t. So time comes out to be u by 2a. U by 2. Simple maths. Time and acceleration comes. Okay. So that is there. Now let's find the power. So the
Sir,
power.
sir,
Yeah.
actually in the previous step, that is not u plus 80, it's u minus 80 because deceleration, right? So
Yeah.
that would then only you get u by 2a, or else you
Yeah.
will get minus u by 2a.
Yes. So yeah. So I here assume that acceleration is negative, so that cancels out. Right? Yeah, but magnitude wise, this is the time, right? Negative will cancel out. Because in this case, if you see, you are right, by the way. The time, if you see, the time actually comes out to be minus u by 2a. But acceleration is also negative. So when I will put the value of acceleration, this negative will get cancelled out.
Yeah, what I told is it's deceleration, so we take a as minus a. That's what I do.
Yeah, this also I can take. Yeah, that also I can do. I can take it as negative. Yes. Okay. Now let's find the power. So power is nu naught. Okay, let's go for the formula. Once you should look at the formula yourself. So the power is this nu naught q square a square by 6 pi c. So nu naught q square a square by 6 pi c. Then energy is power into time. So I write power, I write time, u by 2a. Okay. So I cancel it out and I get this energy. So a and a cancels, u and u cancels. And then finally I put my value of acceleration. Acceleration is 3u square by 8s. Magnitude is 3u square by 8s. So from there I get nu naught e square u cube by 32 pi sc. Let me copy this. Okay, let me copy, because here comes the problem. Here comes the problem. Okay, so let me copy it and paste it here, and let me show you this. Now, do you see that is any option matching? Is any of the options matching or even closer?
No, I got.
So it's not matching, but we are little bit closer. The
So there
biggest
is a
problem, yeah, biggest problem that I see is mass. From where is this mass coming? Any guess? The language is not very clear. The total amount of energy lost.
Electron mass.
Huh? Sorry.
We'll put electron mass.
Yeah, but why we will put anything in this? We cannot put randomly anything in my formula, right? So the language is not very clear, but let's read the statement again. The amount of energy lost to radiation is, as a matter of fact, I think this is wrongfully put in a statement, but as a matter of fact, they are asking the relative energy loss. How much of the fraction of the energy has been lost? So if I divide this number with my initial energy, which was half mu square. So if I do half mu square here, 32 by 2 becomes 16. Pi is pi, s is s, and u cube by u square becomes u, and then sc is sc. Now let me copy this. Let me copy this and let me bring it here. So now you see this option matches exactly. Nu naught e square u by 16 pi mcs. So what they were asking was the fraction loss of radiation. How much fraction of the radiation has been lost. But the language was not very clear. So we got this answer. But then when we look at the option carefully, that mass was there. And that mass could have been come when if we divide it, if we try to do the fraction of the energy loss. So in fact, in this question, they are asking the fraction, and this answer is in fact the true answer, which was given by CSIR-NET. Okay, so keep these things kind of things in mind. Whatever is a change in your option, don't doubt your formula. Formulas are correct. The formulas have been taken from Griffiths. They cannot be wrong. So you have to bring in another thing. So how that thing could be brought? Maybe sometimes English is not clear, then the options give you some hint. Okay, so that has been done here. So we have to divide our answer by half mu square, which tells us the fraction. What fraction of energy is lost in radiation? And we get our answer D. Okay, so that was the last question for today. Any doubts if you have, I'm open for your doubts.